Okay, folks, we're going to go ahead and get started. We have a very special treat today. We have Wyatt Schaubetter with us, and Wyatt is with a company called States Electrical Manufacturing Company. They've been around a long time. They build low voltage and medium voltage switchgear. They have all the UL listings. And I'm sure Wyatt is going to go into a lot of details on that. But what they've been doing recently is producing a lot of switchboards that have a few customizations that have been very beneficial to the folks building solar farms. So I thought we would have a webinar that's focused purely on what they do for the solar industry. A couple of housekeeping issues. This is a webcast, so most of your phones are muted. There is a question mark, I believe, or maybe it's a magnifying glass on the left-hand side of your screen where you can press a button and ask us questions. There's also a chat box. We would love to participate with you and for you to ask questions. We don't want this to be a one-sided presentation. Additionally, we have Adam Norrell joining us from L3 Levine Electronics and Electrics in Alabama. And Adam has used a few of these switchboards, and he'll give us some comments. And now I'm going to turn it over to Wyatt Schaubetter. Wyatt, thank you so much for joining us.
Thanks, Mike. As Mike said, States Manufacturing, we are an OEM of sheet metal and electrical equipment. We are up in Minneapolis, Minnesota, for those of you that are not familiar with us. We're an OEM, so we've been around since 1924. We build standard parts and products throughout the electrical industry. It might be something as simple, realistically, as a small little panel board, all the way up to 35 kV switchgear. And we can do electrical enclosures, we can do really paralleling switchgear, we can do standard switchboards, we have catalog items, we have custom items, is kind of what we pride ourselves on. We are vertically integrated, so we control our whole manufacturing process. We bring in all of our raw sheet metal, raw bus bar, and realistically, we buy all of these circuit breakers and have partnerships with the major equipment manufacturers and UL file extensions from the major manufacturers of the industry to use their components either in their designs to their UL switchboards or in our own customized proprietary designs. With me today, I have John Morin, who is our sales director at States, and John is heavily involved in the solar switchboards in the solar industry as well, and partnering with the developers and the contractors that are typically designing, developing, and then installing this equipment. We do all of our own in-house engineering, both mechanical and electrical. We have right now 6 mechanical engineers and 5 electrical engineers. We have project managers that have engineering background. They have specialty in our ERP system for our resource management. On our shop floor, we have certified welders. We have dedicated machine operators for our laser, turret, water jet, all of our press brakes, and our bus fabrication machines. We do use IBEW is our manufacturing floor. They're a union shop, and that is the same union that the electrical contractors up here in Minneapolis are, which really allows us to pull from a large pool of talented staff when we need to either supplement our manufacturing floor with additional workforce without really having to try and bring in temporary workers. On our production floor, the average tenure of any of our laborers, our machine operators, is 15 years at this point. So we've got a very long running staff here, a very dedicated staff, and very knowledgeable staff. As Mike alluded to, we have over 25 custom UL procedures. So whether it's the panel boards that you'll find at a solar installation, the control panels, metering panels, if it's a custom monitoring panel, what we're going to be focusing on today is going to be a lot of the AC combiner boards, which is dead front switchboards, and then all the way up to the medium voltage metal clad and metal enclosed switchgear. And Mike, our first question of the day for the audience is, do any of you have solar installed at your home or business?
Hopefully you guys should see the poll now. We'll leave that up for about 30 or 45 seconds. While we're waiting on the folks to answer, Wyatt, John, why don't you tell us a little bit about yourselves and your background?
Certainly. This is Wyatt. I am the Director of Operations at States. If any of you are familiar, last name Schallbetter, we've been in the electrical industry a long time. It was actually my great-grandfather that started States Manufacturing. I'm an engineer by degree, so a mechanical engineer. Also do electrical engineering here at States. And currently I am focused on building the company and building our structure throughout the mechanical design process, programming process. John.
Hi, this is John Warren. I am the Director of Sales here at States Manufacturing. I have been personally in the industry since 1980, so I'm getting old, but I've been involved in sales and involved totally basically since 1980 in the power distribution equipment business. So, and for 30 of those 40 years, actually on the manufacturing side. So I guess I've seen lots of different applications and things that have changed over the years and how we apply power distribution equipment.
Great, thanks, John. Wyatt. Okay, I've closed the poll, so proceed.
All right, what we're here to talk about today is solar production. As many of you, I'm sure, are aware, early 2000s and really up until 2005, the solar installations here in the US were really non-existent. You started to see some of the utility scale test sites, some of the thermal sites where you have solar panels or reflective mirrors that were working to focus on a tower, out in Nevada, California, Arizona. You saw a lot of desert applications in the early to mid 2000s, and it was a lot of utility focus. You started to see some residential with solar panels going up on people's roofs, in people's backyards, and you really only saw it in dry type climates. As we got later into the 2000s, into around 2010, we saw a large spike in the drive to cleaner green energy, or the push for renewable energy. As we can see here, it really has been exponential in the scale of utility installations here in the US. 2010, 2015, as I said, that's when a lot of the technological development, incentives by the government really spurred an increase in the deployment of installed solar applications. What we see in the history as we look back is those initial installations had a high volume of cost. It was a lot of very similar but not necessarily standardized design that were being implemented. As you looked across different parts of the country, what different groups of engineers, developers, contractors, manufacturers were putting out in the field was similar in nature but different. And every project you might see in a given week, month, or year would have little nuances to it. And what this caused was a massive spike to capture the incentives in 2015 to 2016 for deployed solar. So in 2016 there, we had a large spike in the installed solar that went in, but we cooled off for 2017 and 18. And what we've been able to attribute this to, and the industry as a whole has attributed this to, is a little bit, is we saw a little bit of a pullback. We saw some standardization in designs. It brought costs down, but slowed down the deployment of solar. For roughly a year, year and a half into 2018, and we saw exponential growth then back into 2018, end of year, all of 2019, and leading up until the end of first quarter in 2020, a large deployment of solar. That is obviously, at this point, we've seen a little bit of a downtick in necessarily moving forward with any projects in the pipeline, but still a large volume of projects in the pipeline. Obviously, some installations have been put on hold while COVID scenarios play out across the country and different states either open up or close their ability to have large groups or gatherings of people. Obviously, the benefit to solar installations is it's almost always outside. In rural or spread out environments where staff can be spread out from people. So definitely a plus for the industry at this point in that most installations can keep moving forward. This is kind of an interesting map. It really shows a little bit about why you guys might be going, what do some guys up in the frozen north of Minnesota know about solar installations? Well, Minnesota actually has a rather large volume of solar capacity that has been installed. And this data is current actually as of the end of Q1 2020. So Minnesota has around 1,400 megawatts of solar capacity installed. And a big driving factor behind that has been a partnership with Xcel Energy, the developers that have come into the state, and the state of Minnesota legislature, making it easier for solar to be deployed in the state. Of that 1,400 megawatts, roughly 700 megawatts is produced by community solar gardens, either managed by a developer or through Xcel Energy or Great River Energy or municipality-based management of the different solar gardens. Obviously, California is a big leader of solar applications. Texas, Florida, and North Carolina, and now New York. We're seeing a lot of solar leads out of those states. Right now, I think John, you could certainly weigh in on this. Illinois is certainly a large target market where developers are going into Illinois.
Yep, we're seeing a couple of different opportunities come from there, as well as New York.
So we're certainly seeing different states here. The less than 1,000 megawatt states seem to be putting more emphasis on catching up to those states that are more heavily deployed at this point. So. All right, our second question for the presentation, Mike. What is your involvement in the solar industry? So are you in the residential side, commercial and industrial, utility, or any of you here interested or participating in the energy storage side of the business?
You guys should see that poll now. I just want to translate real quick. For us Southerners, a term was used earlier. It was roof. And for us Southerners, that is actually roof. So I just wanted to make sure that was clear.
I should say y'all some more, shouldn't I?
Y'all.
Yes, definitely.
Adam's got a much better drawl than I do. I'll let him do that.
Adam, did you figure out your microphone? Yeah, you may not know this, Wyatt, but there's a lot of solar in Georgia for sure. and on so many levels. The incentives, the tax, the tax incentives. At one point you could depreciate the entire solar farm over, I think, a 3-year period. May have even been a 1-year period. I can't remember. Maybe somebody will correct me in the chat box. But there's been lots of incentives. And of course, Georgia Power has had several programs over the past few years where they would offer fixed rates of purchasing the solar power.
Yep, and that's certainly what we've seen the trend up here is Xcel Energy has been a big driving. Obviously, they have to agree to have the different gardens interconnected into their grid, and they have bought on it. Hasn't always been a straightforward, easy process, but I would say, especially within the last 1 to 2 years, as costs have become more known and the price to implement solar has dropped, there's certainly been more buy-in and adjustments, I would say, of that rate negotiation between utility and customers up here as well.
Great. I have closed the poll, so proceed.
So the considerations for the solar gardens that we're going to be focusing on here today is your power. How big of a garden are we talking? Is it going to be a 1 megawatt installation? Is it maybe a couple gardens tied together into a general area, or a little bit of a larger area of installation? Are we talking 5 megawatts? Are we up to utility scale installations where it's 100, 200, 300, 400 megawatt groups? Obviously, multiple groups of strings of inverters and switchboards and metering and transformers all tied together. How are we going to connect to the grid? Is it going to be a DC connection to a paralleling board at DC? Is it low voltage AC paralleling boards? What's our means of protection going to be? Are we going to have fuse conductors, fuse switches? We're going to have circuit breakers. Are there protective relays involved on that main breaker or on the riser pole up to the utility connection? And what are the customers' metering requirements? What are the utility metering requirements? And what different site considerations are there for the installation? At the root design for a grid connection of the different strings is you have a large number of solar panel strings that tie together to an inverter. So the first one we're going to look at is distributed conversion. In this case, there is 1 to however many strings of solar panels mounted usually on the metal framework out in a field that tie to, in this case, inverters that will typically have a DC disconnect on the inverter itself to disconnect an individual string. And then those will step up to AC and parallel at the AC parallel switchboard. At states, we typically see these range anywhere from 1,000 amps up to 3,000 amps. It's driven by the number of strings that an engineer or developer has designed into the size of the equipment. And it's typically nowadays group-mounted thermal mag circuit breakers that are at the AC paralleling level. So if you can see the little highlight where they all parallel together, there's going to be usually group-mounted AC circuit breakers. In between there, where the group-mounted circuit breakers are, and the power grid connection, there's going to be some type of customer metering. There may be a utility metering or monitoring system there as well. And then there's going to be the main disconnect out to the grid. And I'll go through a little bit of the different designs that we've seen and implemented here, as well as some of the options that states can certainly integrate for a customer or utility, depending on the installation requirements. In this connection out to the grid, that's where we start to find differences in an installation or developer requirements, utility requirements on what kind of transformer connection is it. Obviously, it's going to be a low voltage to medium voltage step-up transformer to connect to the grid. Is it going to be a kind of standard pad mount transformer with just air terminal chamber, some load break elbows maybe, or is there going to be any kind of disconnect or fuses in that transformer? Are certainly options that are available. More so nowadays in certain markets, we're seeing reclosers. It could be a pad mount, or it could be a pole mount, excuse me, recloser. John, I think you've even seen some where they're doing a little bit different installation with that.
Yeah, we just want to put them on. They want reclosure. They don't want poles on the site, so they end up using a pad mounted reclosure.
Yep, and it's at this point common to sometimes see the protection for the connection even up at the recloser level, correct?
That's correct.
So, an alternate to this style of paralleling switchboard connection is centralized conversion. In this case, they actually have the strings connected to a DC paralleling switchboard. It could be a single fuse disconnect off each string. I've seen applications where they bring in 2 strings to a single DC connection box, and I've seen where they bring in up to 8 strings of panels to a group mounted DC disconnect box. That DC disconnect box will then typically feed to a larger inverter. That larger inverter will oftentimes still feed up to an AC paralleling board, but instead of perhaps 8, 10, 12, 16, 20 plus group mounted small thermal breakers, you'll end up with 2 to 4 larger frame breakers on the AC board that are connected then to a single main disconnect. Similar things here. Oftentimes there'll be metering up at the medium voltage level. It usually means they're trying to keep the AC switchboard a little bit smaller footprint. In these installations, you often see that the DC disconnects or the group mount disconnects are maybe a wall mount application, or if it's on a skid, they'll have a little bit more compact installation on the DC boards. All right. Another question for you here. Mike, you want to open the poll?
Okay, great. I'm going to go ahead and share this poll just so I think it would benefit everybody to know who's on the phone. So it looks like we've got a nice range of folks. Got some under 1 megawatt, and we have some folks that are doing 100 megawatt installations. So.
Thank you for answering that. All right, here's the AC switchboards that here at States we've been building a significant amount of over the last 3 years. These are just a couple different designs. I'll flip through some slides that we have here. So primary equipment, we talked about, you have the AC combiner breakers. You have usually some provisions for customer metering and a main disconnect of some kind on them up to the utility. Different options, you can add additional sections if utilities require metering within that AC combiner switchboard. You could have another metering. We've seen as many as 3 metering compartments on some of these installations, almost a customer metering compartment, a utility metering between the AC combiner, smaller circuit breakers, the main breaker, and we've seen one then between the main breaker out to the actual transformer connection. You might have a zigzag transformer connection to do a ground creation and do any protective ground fault tripping on the AC board. And certainly an option for a protective relay, if that protective relay is going to be what opens up the main breaker disconnect if there's a fault condition that's detected. Certainly unique feature of states that we think is a big benefit to developers and contractors and installations across the US is because we are in OEM and because of our UL files being fairly open-ended in our construction methods, we can really tailor it to the different utility metering requirements. So if a utility in Minnesota, Xcel Energy has a required utility metering compartment style that they want us to build to, we're going to be able to do that because of our UL procedure. If they want a draw-out circuit breaker, if they want a fixed mount circuit breaker as that main disconnect, if they want a fused visible switch visible blade disconnect switch, we can build that. So we can tailor these switchboards with the components internal to them. Essentially, however, you as the end users or the end users that you are working with need to for the installation across the US. I'm going to take us back in time a little bit here to 2017 is when this drawing was put out. This is an engineering firm that was up here in Minnesota, and this is one of the first kind of, not maybe the first drawing that came out, but a very typical style drawing and installation that was being pushed in that 2015, 16, and 17 timeframe. We see our string inverters. So our groups of solar panels feeding our inverters. Those then would feed at times a paralleling panel board in the initial installations. And then those would feed up to a larger group of thermal mag fixed mount breakers that were group mounted on a panel chassis. I would say at this point, and John can certainly weigh in, but this design at this point was very cluttered. It was kind of new to Xcel Energy, new to the developers up here, and it was, we don't really know what we want, so let's throw a lot of stuff in there. In this case, group mounted breakers. They actually had a utility AC disconnect, so they could disconnect just the group mounted breakers. There was production metering. So this would be Xcel Energy provided CTs and an Xcel Energy meter that was internal to the switchboard. Yep, utility meter there. You had auxiliary load centers. So we had a station control power transformer, group mounted little distribution panel for internal supply power for heaters, for protective relays, breaker power for metering, different monitoring there. We had a grounding transformer breaker. So that's a breaker that's connected to the load bus of the switchboard down to a zigzag transformer. And they actually threw, even on this one, a protective relay. So they had a grounding transformer breaker. It went down to the transformer, and they had a protective relay to the main AC disconnect. At that point, it fed out to the step-up transformer, which fed to the customer's riser pole with a recloser on it, and then there was additional metering up at the medium voltage level that the utility owns. So they actually metered both up at medium voltage level and internal to the switchboard, along with the customer having their internal metering as well. And what did that look like? That looks like a bunch of different compartments all tied together. So the original designs that we saw a lot of, and states participated in putting some of these in the field, ended up being very cube-like. The initial design development kind of resulted in 2, 3, 4, usually front to back, sometimes side to side, top to bottom, cube type designs based on what was being proposed by developers, proposed by engineers in the deployment of these solar systems. These construction took a little bit more. They wanted fully welded construction in this environment. So we were able to do some different compartmentalized welded type construction with barriers and viewing windows from the outside as they required on that. When we do a switchboard, we'll actually do a takeoff. So if you recall from the last drawing, there's actually flowed left to right. Well, the beautiful thing was when they called us and told us we actually meant to go right to left, we were able to very easily, because of how States is set up, flip the 400 amp combiner breakers to the right side, have the AC utility AC disconnect switch in the right side of the cabinet, and we're right to left instead of left to right as the engineer's trying to show. As you can see, then we have the different disconnects, we have different feeds out to the utility metering, and then the station power as well. So this is what was for a number of installations and a few years in the initial boom of the solar market here in Minnesota, a very typical installation for States. Since then, this drawing is here out of January 2020. We've seen a migration to a little bit more of a clean, less cluttered installation, or I guess you could say they divide up where components are installed a little bit different. So this is a US solar based application. If you're familiar with any of their setups, this is a very typical proposal for US solar. Here we have a string inverter, and this is our 1 to the N inverters, depending on how many you want. That inverter feeds up to group mount 175 amp group mounted thermal mag circuit breakers. So that's where our AC paralleling is occurring at the switchboard level. The switchboard has no metering between those group mounted breakers necessarily and the main disconnect breaker. So that 1600 amp breaker is the disconnect out to the utility. They instead have the customer metering, and utility metering is between the main disconnect breaker and then out to the transformer and up at the medium voltage level. Similar to that original installation we showed you, there is a zigzag transformer at the top of the customer print. That has been cleaned up a little, where in this installation they do not have a protective relay. So that little circuit breaker connecting to the zigzag transformer is what, in the event of a fault condition, will trip open the main breaker and disconnect it from the grid. In this case, the transformer is a 600 to 13.8 conversion. So the paralleling on the AC board is being done at 600 volts. With our switchboard file, we can do up to 1000 volts under UL 891, but realistically, most UL circuit breakers max out at around 690 volts. So you're not going to typically see a UL installation up to 1000 volts yet. It is certainly within the works of the major equipment suppliers to get to that level, but typically 600 volts is going to be the maximum AC you're going to see in one of these switchboards.
And 600 volt is what they seem to now design most of these systems to.
Correct. Yep.
Versus a couple of years ago where 480 volt was common design.
Correct. Yep.
So we are pushing it.
What does that look like? This is also part of that same specification. In this case, they've done a little bit of a pad layout, and the engineer's proposing that medium voltage step-up transformer next to, they've gotten away from the cube design typically in these installations now, and it's more of a standard switchboard style construction. They're typically used to a flow either left to right or right to left, depending on the orientation of the site. And that obviously is a big play in how are they routing the conduits on a site? Are the strings flowing left, right, east, west, north, south? And so we can on a project have some switchboards that are orientated in one direction and some that are orientated in the other direction with our modular construction. Typically on that same pad, you're going to have the zigzag transformer and you're going to have an auxiliary rack where oftentimes that's where a customer is going to be mounting their metering components. So here, instead of the short, stubby, little cube type design from those original 2017s, much more typical for what we do now is a standard switchboard construction. Obviously 3R construction is going to be the most common type construction for us. All of our 3R construction is actually gasketed and ventilated with gasket and filters is our design standard for these. Out in the field during the construction process before native vegetation kind of takes back over, you're going to have a lot of dust, a lot of dirt, and a lot of grime. So those ventilation louvers on the front are louvered, and there's a metal mesh screen behind it, which really does keep the equipment nice and clean for a long number of years, because it remains to be seen how great the maintenance is on these switchboards that are sitting in fields all across the country. Once we get to the inside of it, this is where states can really shine in our customization for what does the engineer, what does the developer want for a layout. In this case, they were requesting that the group mounted breakers be directly essentially tied into the main disconnect, and then that feed over to different metering compartments. So we're able to stack a main breaker in a 1600 amp up to 2000 amps directly above the required number of inverter breakers where they're doing the paralleling. And then on one side of the compartment is going to be a production meter that the customer had requested we provide on this with PTs, CTs. We have an auxiliary transformer cabinet where we would have some control power, station power, distribution panels to power up the meter, power up the circuit breaker, and then utility metering and a customer metering compartment for installation of any of their components as well. Similar in nature, this system, bigger installation, 2500 amp main breaker disconnect, and more combiner breakers. So we have, again, 3 sections, but here we have more group mounted circuit breakers, and the main breaker is shifted into a different section just due to required mounting space. Still provide multiple different sections worth of auxiliary station power, distribution panels, and customer metering and connection. Like you saw before, we still provide different one lines for the actual installation of the equipment. So this is standard application from states. We'll provide you with the 1 line, 3 lines, control wiring schematics. We provide interconnect diagrams for the end user, the customer, terminal block layouts for any of their DAS equipment type interconnection. We can provide UPS if there needs to be backup power in the event of an outage. So we'll provide a little industrial control panel rated UPS. As I said, flow through the different 3-line diagrams, group mounted breakers, the main breaker, and then any of the station power. We, in this case, even can do multiple station control power transformers. And oftentimes we see this being the case because you'll need one that is 600 down to 480, 277 if there's different motor control. I think they had some different fans on this installation, tracking motors. You know, maybe 480 volts required to power up different parts of the solar string as they rotate the panels to get the best angle to the sun. And then you still need to get down to 120, 240 to either power up a meter, a protective relay, or the customer's metering system. Anything you want to weigh in on there, Mike or Adam? Okay.
No, keep going.
As I said, states, we really, with the way our UL procedures are written, we can tailor those internal components, whether you have a customer requiring a specific digital meter, a specific UPS to provide power, or if they give you just make sure we have power for our control components for an hour, 2 hours, 3 hours, 4 hours, whatever it may be, we can design your control system to meet whatever your needs are.
Yeah, I guess I'd like to ask the audience a question, and you guys can just answer in the question box or chat box. You know, are these customizations something you find helpful? Do they seem to be required on some of the projects you worked on? Do you wish you had this ability on a previous project? And we'll let them answer while you're talking, Wyatt.
Certainly. Similar in nature, different developer, different engineering group, but as we said, this is again late 2000, or I guess mid 2019 in this site here, but very similar layout to some of the drawings we've just reviewed and some of the designs we've just reviewed. We have strings of inverters to an AC combiner board. In this case, though, what is perhaps a little more difficult to see is the board was essentially a blank slate, and the customer metering, the station power, the different disconnects were grouped outside of the switchboard. I should say the main disconnect still resided within the AC switchboard, but most metering was located outside of it. And what that ends up doing then is oftentimes it'll just be a 2-section instead of a 3-section switchboard lineup. So you'll still end up with group mounted circuit breakers. You might have a miniature breaker feeding over to a station control power transformer that might be a 3R type transformer that the contractor is either installing on a pad, or we've certainly seen them hanging on the side of the switchboards out in the field. And then simply a main disconnect breaker that, once again, they might have a protective relay, a zigzag transformer breaker connection, and then still there is room in the different compartments for customer metering to be inside of it. A lot of the times, though, we'll see in the field they actually end up mounting them either on a pedestal or unistrut to the side of the equipment when they do a little bit smaller footprint installation like this. Obviously, it's certainly an option to do it this way and then have 3R mounted components and equipment, but as you saw in those 3-section lineups, a little bit cleaner perhaps, or easier installation, knowing that everything is internal to the switchboard. That equipment can arrive on site fully bussed together, fully bolted together. Interconnects can be run between everything if you do it that way. And that's certainly a question I would also like to pose to the group, Mike, is those that are involved in the installation process, what kind of benefits you see to equipment arriving all together. So if you are capable, certainly, of handling that equipment on site, or do you wish you had the capability of handling the AC combiner boards on site with them shipping from our factory all in one piece? We certainly see, I think, more contractors here in the Midwest liking that the equipment shows up 2-3 sections bolted together. Obviously, it hinges largely on what your site conditions are and if you have the equipment on site to handle that type of installation. But do you find value in that? Do you wish you had that ability? Do you have that ability is what I would pose you as a thought.
Yeah, and maybe even to further expand that, I mean, building all this equipment into structures that can be mounted together, but to Wyatt's point, do you like the them in a single shipping unit, or would you rather have individual sections shipped as individual sections to be bolted together in the field?
And then multiple boxes to lose in said field.
Yes. But it wasn't uncommon prior to a lot of these more standard designs that we've kind of come up with to be in the field and just to see a lot more racking and individual components all over racking, and people, you know, doing a lot of work in the field versus setting a piece of equipment and really start to be able to hook up their inverters, right? You know.
Yeah, a lot of field assembly if you ship it all separate, obviously, and have different components coming from different suppliers. Right. And that's what we're going to kind of hinge on right here and certainly touch on. Again, more recent, newer project here, and this is where I would like to certainly highlight the benefits that I think we see and L3 sees in working together with a company like L3 and states in collaboration to get the end users a complete system package. This application, this project, has utility primary metering. There's a recloser up on the pole for the utility. There's a fused disconnect switch. We have a solar recloser, a pad-mounted solar based recloser for the solar application, that is. I think John touched on that. At times they don't want to have that recloser up on a pole, so they'll do a pad mount enclosure instead. You have customer primary metering. This could be just a simple CT PT cabinet that's mounted on a pad. You have a transformer, a main circuit breaker in the switchboard, and then our AC combiner switchboard with the ancillary power control centers, zigzag transformer, and all the same devices that we've highlighted here. The benefit that we see in working with us at States and L3 in collaboration on a project is all of those different devices. We can handle the collaboration between bringing either all of the devices into States that make sense to build into that AC switchboard, or build into the customer primary metering, the solar system AC disconnect at the medium voltage. Our breadth of our ability to produce product allows us to either A, produce that product in-house, or use the specialties that L3 has in their supply chain to source you a transformer. We can source the reclosers, we can source the different metering, and provide one single point of contact and communication to the end users. Same project, just a different switchboard. I talked about this a little bit. Your different metering, different controls, oftentimes will be different PTs, CTs. You might have a UPS, a relay that you need to connect to. We can do different protective relay functions, either off of a breaker that opens, and when that breaker feeding the zigzag transformer opens, it might trip the main breaker, or a zigzag transformer might have a residual kind of ground fault detection type CT connected, and that is what opens the main AC disconnect. Transformers, oftentimes you're going to see the pad mount step-up transformer might be at 15 kV, it could be a 25 kV, 27 kV application, and even up to 35 kV. Oftentimes it's anywhere from 750 to 3000 kVA on that. Obviously it depends on the size of the solar installation. Do you have a 1 meg, 5 meg, multiple different strings? What is it? A zigzag transformer, and then all of the different control power transformers. Either between L3 or States' relationship with our vendors as well, outside of our normal scope of supply, we can supply all of those different transformers, either through L3's relationships or our relationships. And I certainly want to highlight because I think, John, you're sort of seeing more of this, that up at medium voltage, it's becoming more and more common to have customer metering or the utility metering up at medium voltage. And as I highlighted before, one of our key components is our customization. Our UL files are very all-encompassing, so we can use our general construction methods and construction standards to really tailor an application to what you need to supply to your end users, your customers. If you need disconnect switches, you need PTs, CTs, maybe they want to do a drought circuit breaker or a switch and breaker combination, a switch and fuse combination, a DC battery system inside of them to provide the power to said circuit breaker, the control power transformers up at medium voltage are all within States' ability to supply you a end installation solution. Here, just highlight a couple of our different construction methods. This one was actually a medium voltage switch on one end of the installation. That was the actual utility disconnect. The utility required simply a load break visible disconnect switch. And the customer actually had a PT compartment, a CPT compartment, and then a drought circuit breaker is what the customer on this one wanted to actually be able to disconnect their system as well. Simple one line there. Substation feeder, the solar plant equipment, and the different metering and protective devices on that installation. And this was a solar garden project here in Minnesota that at 35 kV we built different XL energy metering bays per XL's requirements, and then had main disconnect switches for the utility, and the different meters for XL were located on the end of the equipment. Where you can see just simply different PTs and CTs throughout the different metering bays, and then hook stick operated fuses, and that's the application. As we said, we can certainly source the reclosers as well for customers if they need them for their installation. Kind of wrapping up here, we talked about why States, why L3. I think between our manufacturing experience, our design experience here at States, engineering experience, we are familiar with the DC disconnect side. The AC combiner switchboards is certainly kind of our bread and butter. Customer metering, utility metering, the different transformers and reclosers. Obviously, L3's got a very strong partnership in the transformer world. They can get the different transformers, the different medium voltage equipment that's required on these sites. They have multiple sources that they can lean on to meet whatever the end installation requirements are. And then the question is, what comes next? Mike, I think you weighed in. There is obviously a substantial amount of solar down in Georgia. And what I've tried to highlight here from the same Solar Energy Industries Association is, here's our different view, current as of this year, for the operating, under development, and under construction projects across the US. What I find it certainly very interesting about this map is yellow is the currently operating sites. Orange and red are not actually up and running necessarily yet. Maybe a portion of the project is up and running, but it's not actually up to full scale yet. So there is a substantial amount of development across the entire US, especially on the eastern seaboard, that is still being installed today or still being developed in the design phase. A little bit of data from SEIA. Right now, they are projecting through 2025 a fairly steady deployment of around 13 gigawatts of solar each year. That's kind of what they've foreseen as the sustainable deployment of solar applications through 2025. With that, there's over 50 gigawatts that are already designed, engineered, in the pipeline to then go out and procure the end user installations across the US. Quite a bit of upcoming solar deployment yet to occur. Certainly what's a little bit interesting as you look up in the Midwest, where we are doing a lot of these switchboards, these are the 1 to 5 megawatts. It's a very typical installation up here, and a lot of this is where you see the different AC combiner boards. So certainly across Minnesota, Illinois, Indiana, Ohio is where we see a lot of the 1 to 5 megawatt installations that'll have different AC combiner boards, the different transformers. And as we migrate down to the southeast, obviously North Carolina has a large volume of those same size installations. And as you start to move further south, you start to see more of the, what is oftentimes a utility scale 100, 200, 300, 400 megawatt installation. Quite clearly there with the red indicators, quite a few large scale developments in Georgia and northern Florida as well that are under development. That's what I got for everyone. Obviously, if you have any questions at this point, certainly feel free to post them, and Mike can weigh in and Adam can weigh in if they want to touch on anything right now.
Okay, there was a general question that came in that's kind of interesting. Not sure if you guys will be able to answer it or not, but so it's in reference to Georgia Power Company is highly resistant to net metering. And if they ever permitted it, they would only offer a fraction of the dollars per kilowatt hour of what you actually pay. Is this the same in Minnesota or California? Do you know anything about either state?
I can't speak to California. What I can say is the state of Minnesota has, they've certainly tried to work with Xcel Energy as the prime electrical power company here in the state. They've tried to work in collaboration and to have everyone play nice. And there was certainly in the early days a little bit of, I think, heartburn back and forth. But at this point, it has, for all intents and purposes, been legislated in that they do need to accept the net metering and they do need to work together. And I think Xcel Energy has certainly started to buy in more. They've accelerated with the substantial deployment of solar that we have in the state and the wind that we have in the state. Xcel Energy has actually accelerated their decommissioning of all coal plants in the state of Minnesota. Originally, I think they were slated through 2035 to keep all of the different coal plants operating, and via the different solar applications they're bringing online, some natural gas applications they're bringing online, and the nuclear energy we have up here, I think they've accepted that they should kind of get on board with the transition to solar energy and different energy sources. And at least here in Minnesota, they're playing pretty nice at this point. I don't know about California, but who knows with that, right?
Sure. You guys do UL 891 and also UL 1558?
Yep, you certainly don't see, at least I haven't to date seen UL 1558 in a solar application. 1558 low voltage metal clad switchgear is certainly the, I guess I'll call it more robust. It's going to be drought circuit breakers for everything. So typically you're going to see that in a lot more industrial applications, data center type environments, healthcare type environments where they're looking for more robust structure. Compartmentalized construction, barriers between line load connections, barriers between phases.
Well, fantastic. This has been very helpful. If there's any more questions at a later date, feel free to email us. Thank you, Wyatt. Thank you, John, so much for your time. It was very informative.
Yeah, thanks, Wyatt. Thanks, John. Good job, guys.